Okay, so this will be a video on geometric and actually any type of series, but when they are infinitely long and have an infinite number of terms. So before we get into that, I just want to get into a quick review. These are an example of each of the two types of sequences. So hopefully you're recognizing sequence A there with the pattern of +2 and sequence B with a pattern of ×2. So that makes sequence A be arithmetic and B is geometric. Okay, so just as a review, just to make sure we're where we should be able to write explicit formulas for A sub n. And just remember A sub n for the arithmetic is 3 plus 2 times n minus 1. And that could be simplified. You could distribute the 2 and combine terms. And for the geometric, we are at 3 times 2 to the n minus 1 power. Okay, those formulas, again, explicits are used to find any term in the sequence, right? So when you want the 30th term without having to list the entire sequence, you can simply plug in 30 for the n, and you can verify the answers on those. We should be getting 61 for the sequence A, and then sequence B, since you're multiplying by 2, those numbers get really, really, really big. So huge number there. Okay, and then the most recent material was about finding the sum of the terms. So if I ask you for the sum of the first 30 terms, that was the two new formulas from previous sections. For arithmetic, again, remember it's n over 2 times a1 plus an. So you can see the values plugged in there, 30 over 2 times 3 plus 61. So 960 would be the sum of 30 terms. And in geometric, it's a1 times 1 minus r to the n, all over 1 minus r. Okay, so go back and look at the previous videos if those formulas, if you want a little extra recap on those. But again, these numbers are the sum now of 30 terms. Okay, so let's keep moving. Let's think about if the series, or if there was an infinite number of terms, right? This thing just went on infinitely long. Would we be able to find a sum? Okay, so let's think about, again, what S1, S sub 2, S sub 3, those are called partial sums because they're the sum of the first n terms. So for example, the sum of the first term is just the first term. Okay, the sum of the first two terms is the 4 plus the 8, or 12. Okay, the sum of the first three terms, 4 plus 8 plus 12, is 24. So as this thing goes on forever and ever and ever, what would that sum end up being? Okay, and hopefully you're seeing this thing is just growing bigger and bigger and bigger. So this thing would actually just go to infinity, and it would not have a real number sum. Okay, so the definition on that, there's a term for that. This one would actually be said to diverge, because the definition here is a sequence or series is said to converge if it approaches a single real number. Okay, infinity is not a real number. Okay, so since this one's sum was infinity, we would say that it diverges. Okay, so we will see in a few minutes when is it possible to actually converge. It might not seem like they ever will. If you're adding up an infinite number of terms, how could it ever converge to a real number? But we shall see. Okay, so another example. Actually, let me go back for 1 second. This example was supposed to illustrate that, and hopefully we can see any arithmetic sequence like this one. This one had a common pattern of +4, right? So when that happens, if you have an arithmetic sequence, you're just going to be adding. So each term is going to get bigger and bigger and bigger and bigger. So those will actually always converge to infinity. Ooh, that was, or they may go to negative infinity if your common difference was a negative number. Okay, so an arithmetic sequence, if it's infinitely long, will always diverge. Okay, what about geometric though? Let's look at this example. This is a geometric sequence of 3 to 6, so we're multiplying by 2. That's going to be our common ratio here. Okay, and that one should look very familiar to similar to the last one. These terms are just going to grow and grow and grow and grow. So when you're multiplying by 2, the numbers are just getting bigger and bigger and bigger. So this thing's going to go to infinity as well, and we would just say it diverges. Again, there is no sum, okay, because it's going to infinity. All right, so let's think about, could we ever get something to converge? Here's kind of a good classic problem I always like to use here. Okay, like something you can visualize. So imagine you're standing here. Okay, 20 feet away from the door, right? 20 feet from the door to where you are, okay? And here's the situation. You want to eventually walk to the door, okay? But you're going to do this in a very unique way. Okay, so for example, you're going to start where you are, and the first thing you're going to do is you're going to walk halfway to the door. So you're going to walk to maybe about here. You're going to walk 10 feet, in other words, right? Okay. Then from where you are, you're going to walk half of the remaining distance. So if you're at 10, you're going to walk another 5 feet. Okay. And you're just going to keep doing this. You're then going to walk half of that 5 feet. You're going to walk 2.5 feet. And then you'll just continue to do that over and over and over. And the riddle, the way that makes it kind of a riddle is like you would actually never get to the door because you would need to walk through an infinite number of points. You know, when you're 1 inch away, you still have to walk half an inch, then a fourth of an inch, then an eighth of an inch. So it's like this never-ending, you know, set of terms. So the idea is if we were to add these lengths together, okay, half of that's 1.25, and just keep going infinitely long, forever, would it actually add up to something and have a sum? And the answer is yes, it should add up to the 20 feet, shouldn't it? So it actually does. Okay, so that's an infinite number of terms. And it does actually have a sum, and I want to talk about how we could find that. Okay? All right, so let's dig into this example a little bit more. Okay, here's our sequence again. It's definitely geometric, right? Because we are actually multiplying by 0.5 each time. Okay, so it's a multiplication, right? It's a common ratio times 0.5 times 0.5 times 0.5. So let's find some partial sums. What would be the sum of the first 6 terms? Okay, to do that, I had the formula from the other day, from the previous lesson. It's always a1 times 1 minus r to the n over 1 minus r. Okay, that's the sum of a geometric series, right, from a previous section. So for this example, a110, 1 minus 0.5 to the n, which is 6. Oops, sorry, this board's getting a little bit off here. Okay, 1 minus 0.5. Okay, so let's try that again. We have some technical difficulties. First term is 10 times 1 minus 0.5 to the 6th power, all over 1 minus r, or 1 minus 0.5. Okay, so we calculate that out and get a value. Okay, so let me grab a calculator here. We got 10 times, make sure you're using the parentheses and enter it just as written. Parentheses in the numerator and in the denominator. I'm getting 19.6875. Okay, so that would be the sum of the first 6 terms. Okay. What would be the sum of the first 15 terms? So only difference here is our n value is now 15, right? So that's going to be first term 10, 1 minus 0.5 to the 15th power over 1 minus 0.5. Right? The only difference was the exponent there, right? So let's do that one real quick. Let's see what we get. Okay, that one I'm getting around 19.99939. Okay. So if we were to add up 15 terms, you see this thing's getting very, very close to the 20 that we said it should be in theory. Okay, so as n's getting larger and larger, this thing is approaching 20. Okay, let's talk about how would we get that number. Okay, this is a way to kind of approximate the infinite sum. Just keep making n larger and larger and see what the sums approach. Okay, but there is an actual way to get the true infinite sum. All right, so let's think about this again. Formula, right? A1 times 1 minus r to the n over 1 minus r. That gets you the sum of the first n terms, right? Just use that. Okay, our question though is, what happens as n goes to infinity, right? Because we want to know eventually what's the sum of an infinite number of terms. So first off, a little property here, this thing will only converge. Okay, if we remember back a couple of previous problems, in this one it was geometric, the ratio is times 2, right? We said if you're multiplying by 2, the numbers are just going to grow and grow to infinity. The only reason our example had a sum was because our ratio, the thing we were multiplying by, was less than 1. Okay, that's causing the terms to get smaller and smaller and smaller, so that eventually you're really adding like nothing. You're adding such small amounts out here that the sum as a whole is closing in on a real number. Okay, so that will only happen, you will only converge if the ratio is between actually -1 and +1. Okay? Otherwise, the thing will diverge to infinity. Okay, so that's the trick to see if it's going to converge or not. All you got to check is are you multiplying by between -1 and 1? Okay, and the idea is when that happens, that term, okay, let's say for example r is a half, like our example. If r is 1/2, and you raise this thing to a really, really big power as n goes to infinity, think about 1/2 time to a big power, right? It's 1/2, 1 after the second's 1/4, 1 after the third's 1/8, then 1/16. This thing actually just reduces down or approaches 0. Oops, not s, let's go zero. Okay, so this whole term kind of just disappears. So the formula, the same formula, just becomes a1. It would be times 1 minus 0 over 1 minus r. Okay, and what is 1 minus 0? 1 minus 0 is just 1, right? So this formula is really just a1 times 1 over 1 minus r. So that formula, okay, that formula right there will give you the sum of an infinite number of terms, as long as r is between -1 and 1. Okay, so let's do an example. Let's take a look. Let's verify the one we did. Let's not do that, but using the previous example of 10 plus 5, the one with we're walking to the wall here, right? Just to verify that it works. If this went on forever, the infinite sum is just a1 over 1 minus r. And in this case, the r value to get from there to there was multiplied by 0.5. Okay, so that means the sum of the infinite number of terms is 10 over 1 minus 0.5 is 0.5, and 10 divided by half, that's how we get the total number of 20. Okay, let me just walk through one last real quick one. If you think about this example here, okay, I just made up a sequence. I started with 7, I multiplied by 0.6. Okay, remember, it must be between -1 and 1. So I just chose 0.6 as my ratio. Got a couple terms. Now, if we want the total sum of an infinitely long string, remember our formula is a1 over 1 minus r. So that's all we got to do is 7 over 1 minus 0.06. So 7 divided by 0.4 gets us our sum. And this thing would actually add up to 17.5. Okay, an infinite number of terms would add up to a real number, 17.5. All right, and that only converged because, again, our r value, I chose something between -1 and 1 for the ratio. Otherwise, we say it just diverges and there is no sum. Okay, so hopefully that helps. That is infinite series and how to find the sum.